As scientists, you'll be making many quantitative measurements, so you want to remember that every measurement involves error or uncertainty. Lord Kelvin, who had a temperature scale named after him, said that when you can express a measurement in numbers, you know something about it. But when you cannot express it in numbers, your knowledge is of a meager and unsatisfactory kind. Scientists have measured how big or small things are, from the size of the universe to the size of a hydrogen atom. Scientists have measured how hot or cold things are. The center of the sun is really hot, 15 million degrees Kelvin. Water freezes at 0 degrees Celsius. Scientists can measure how fast or slow things are. Note that chemistry ranges from 0.1 picoseconds to, a few days. Whether at home or in the lab, you've made measurements, so stop the video and fill in the blanks. And the answers are, good job. So let's practice determining the number of significant figures and the uncertainty in a number. 16.00 represents the number used in chemistry, so stop the video and answer these two questions. And the answers are, the last significant figure represents the uncertainty or error in the number. This number represents the atomic weight or molar mass of oxygen. So just to make sure we're on the same page, let's review the significant figures rules. So stop the video and identify the rule that we applied in the number 16.00 in the last slide. And the answer is, the last significant figure is the digit which has the error or uncertainty. This digit is in the hundreds place. That means the uncertainty is plus or minus 0.01. Let's practice. Stop the video, and for these three numbers, determine the number of significant figures and the uncertainty. Here are the answers. Remember, the last significant figure is the uncertain digit, that is, the digit where there's error. Let's apply these ideas of significant figures and uncertainty to an actual measurement. You want to measure 10 mils of water using these two volume measuring devices. So stop the video and figure out how you would report the volume using significant figures. Use this hint. Here are the answers. For the beaker, each line on the beaker represents 10 mils. That means the tens place is the digit we know with certainty. That means we can guess at the ones place, which is the uncertain digit. For the 10 mil graduated cylinder, each line represents 0.1 mils. That means the tens place is the last certain digit. That means we can guess at the hundredths place, which is the uncertain digit. You reported the volume of 10 mils of water using each volume measuring device. So stop the video and report the uncertainty in each volume. And the answers are, so remember, the last significant figure is the uncertain digit where the error lies. Remember, when you make a measurement, the error in that measurement has to be reflected in the number that you report. So stop the video and answer these two questions. And the answers are, for question 1, since each line represents 1 milliliter, you're allowed to guess at the next digit. That'll be the tens place. So 10.0 milliliters tells you that the uncertainty is plus or minus 0.1 milliliters. For question 2, 10 mils has one significant figure. The uncertain digit is the tens place. So each line on the beaker likely represents 100 milliliters, or in the hundreds place. Remember, each line on the 10 mil graduated cylinder represents 0.1 milliliters, and in the 100 mil graduated cylinder, each line represents 1 milliliter. So note that the uncertainty in those two measurement devices is much lower. So make a prediction. Which volume measuring device do you think gives a more accurate measurement? Which one gives a more precise measurement? Usually the device which has the smaller uncertainty will give the more accurate measurement and the more precise measurement. So the answer for each question should be the 10 mil graduated cylinder. Measuring devices need to be calibrated. That is, we want to correlate the readings of an instrument with those of a standard, check how accurate the instrument is. So stop the video and figure out how you would calibrate your finger and how you would calibrate a beaker. So this picture shows how a ruler can be used to calibrate your finger. So if you assume that each crease on your finger is 3 centimeters, and 3 centimeters on the ruler is slightly different, how would you answer this question? And the answer is, so using your finger to measure length leads to a systematic error and poor accuracy. We can identify a substance by measuring the wavelength of light emitted or absorbed by that substance. Light detectors are calibrated by using the mercury emission spectrum green line at 546.1 nanometers. A person's blood glucose is measured using a glucose test meter. The meter involves electric current. The current is directly proportional to the glucose concentration, so that needs to be calibrated too. So as scientists, we want our measurements to be accurate, that is, close to the true value. And when you do a series of measurements, you want your results to be precise, that is, close to each other. So stop the video and answer this question. And the answer is precision. Here's some data measuring the density of water using 2 measuring devices. So stop the video and answer these 2 questions. So here are the answers. Note that the first set of data has less scatter. So measuring device 1 is more precise. For accuracy, we have to measure the average density for the 6 densities measured for each measuring device. The average density that is closer to the true density gives us the more accurate measuring device.